Imagine a pitch-black, storm-tossed night in the Philippine Sea, where 20-foot swells crash violently against the steel bow of a warship driving hard through the ocean. Salt spray whips across the bridge windows. The deck plates vibrate with the relentless hum of tens of thousands of shaft horsepower, and the radar horizon is cluttered with the faint electronic whispers of distant aircraft. Here, in the unforgiving environment of the Indo-Pacific, the United States Navy relies on its absolute workhorse, a vessel that has come to define modern maritime dominance over the last 30 years. This is the Arleigh Burke class guided missile destroyer, a marvel of naval architecture that can track hundreds of airborne targets simultaneously, hunt silent submarines in the deep, and strike land targets 1,000 miles away. Yet, beneath the gray paint and the bristling array of antennas, this undisputed king of the surface fleet is quietly suffocating under the weight of its own evolutionary success. The paradox of the Arleigh Burke class is one of the most fascinating engineering dramas in modern military history, presenting a central conflict that the Navy can no longer ignore. This warship is widely considered the most successful surface combatant built since the end of the Second World War, yet it is currently facing an existential crisis because it has effectively run out of room, weight capacity, and electrical power. Naval architects have spent decades brilliantly cramming newer, heavier, and more power-hungry technology into a hull that was originally drafted in the 1980s. Today, you cannot fit any more advanced active radars, high-energy lasers, or heavier hypersonic missiles onto this ship without critically breaking its stability or exceeding its electrical generation limits. The ultimate defender of the aircraft carrier strike group has been pushed to its absolute physical limits, creating a dangerous vulnerability just as the threat of drone swarms and supersonic anti-ship missiles reaches a historical peak. Understanding how a multi-billion-dollar warship reaches the absolute end of its developmental rope requires looking back at the fundamental design philosophy that birthed it during the late stages of the Cold War. If detailed technical breakdowns of naval architecture and maritime strategy interest you, subscribe. I have got more of these coming. The original Arleigh Burke was designed with one primary, terrifying scenario in mind: surviving a massive, overwhelming wave of Soviet supersonic bombers launching dozens of anti-ship cruise missiles simultaneously. To defeat this apocalyptic saturation attack, the Navy needed a ship built around the Aegis combat system, a revolutionary integration of computers, radars, and interceptor missiles that could automatically track and destroy multiple targets faster than any human crew ever could. To carry the heavy flat-faced arrays of the Alpha Nook Sierra Papa Yankee 1 passive electronically scanned radar, the designers had to abandon the fragile aluminum superstructures used on previous destroyer classes. Aluminum had proven disastrously vulnerable to fire, a lesson the Navy learned the hard way after the devastating collision of the cruiser Belknap and the horrific ship fires suffered by the British Royal Navy during the Falklands War. Therefore, the Burke was built from the keel up entirely out of steel, creating a rugged, blast-resistant citadel that could take a hit and keep fighting. However, wrapping the massive Aegis radar arrays in thick steel armor placed a tremendous amount of weight very high up on the ship's superstructure. This immediately created a severe center of gravity challenge for the naval architects, who were forced to design a remarkably wide beam, the width of the ship, to prevent the heavily laden destroyer from rolling over in rough seas. This exceptionally wide hull form provided the essential stability required to carry the heavy radar panels, but it instantly introduced the first of many operational penalties that the crew would have to endure. A wider beam inherently creates more hydrodynamic drag, meaning the ship requires vastly more power to push through the water compared to the sleek, narrow destroyers of the past. Furthermore, the wide, flat-bottom nature of the hull gives the Arleigh Burke a notoriously stiff rolling characteristic in heavy weather, snapping the ship back to an upright position with a violent, jarring motion that is physically exhausting for the sailors living aboard. While this snap roll ensures the vessel will not capsize in a massive North Atlantic gale, it turns the interior of the ship into a bruising environment where crew members must constantly brace themselves just to walk down a passageway. To overcome the massive hydrodynamic drag of that wide steel hull, the engineers had to pack the engine rooms with an overwhelming amount of raw mechanical power. Propulsion on the Arleigh Burke class relies on 4 General Electric Lima Mike 2500 marine gas turbines, which are essentially modified aviation jet engines harnessed to turn massive steel drive shafts. These 4 turbines are split between 2 entirely separate, watertight engine rooms, ensuring that a single torpedo or missile hit cannot completely cripple the vessel's ability to move. Together, these screaming turbines produce a combined 100,000 shaft horsepower, driving 2 enormous controllable pitch propellers through a set of highly complex reduction gears. This staggeringly powerful propulsion plant gives the 9,000-ton destroyer the acceleration of a sports car, allowing it to surge from a standstill to speeds well over 30 knots to keep pace with nuclear-powered aircraft carriers. But to achieve this incredible speed and acceleration, the Navy had to accept a dangerous and incredibly costly compromise in the realm of operational logistics. Gas turbines are notoriously thirsty engines that guzzle marine diesel fuel at an alarming rate, especially when the ship is operating at lower, more economical cruising speeds where gas turbines lose their thermodynamic efficiency. Because the Burke class consumes so much fuel just to maintain its station in a blue water environment, it is permanently tethered to the Navy's fleet of massive replenishment oilers. Every few days, regardless of the weather conditions, the destroyer must pull alongside a massive supply ship, shoot over heavy steel cables, and hook up fuel hoses while both vessels steam at 15 knots through heavy ocean swells. This complex ballet of underway replenishment is one of the most dangerous routine operations in the fleet, and it is a direct consequence of choosing high-performance gas turbines over more fuel-efficient but slower diesel engines. While the main propulsion turbines drive the propellers, the lifeblood of the ship's combat capability relies entirely on a separate set of engines dedicated to electrical power generation. Initially, the early Arleigh Burke destroyers were equipped with 3 Rolls-Royce Allison gas turbine generators, each capable of producing 2.5 megawatts of electrical power. This massive electrical grid was necessary because the original Alpha Nook Sierra Papa Yankee 1 radar system requires staggering amounts of electricity to blast its radio frequency energy out into the atmosphere. The radar does not physically rotate. Instead, it uses electronic phase shifting to steer multiple radar beams across the sky in fractions of a second, a process that generates massive amounts of waste heat. Therefore, alongside the generators, the ship had to be fitted with enormous, power-hungry chilled water plants just to keep the radar computers from melting down during a combat engagement. As the geopolitical threat landscape shifted into the 21st century, the Navy realized that simply tracking aircraft was no longer enough. The destroyer had to become a versatile, multi-mission platform capable of hunting submarines with organic aviation assets. This operational demand led to the creation of the Arleigh Burke Flight II Alpha variant, which fundamentally altered the physical silhouette of the ship by adding 2 massive helicopter hangars to the aft deck. These hangars allowed the destroyer to permanently embark 2 Romeo variant Seahawk helicopters, extending the ship's anti-submarine and surface search range by hundreds of nautical miles. However, the addition of these cavernous steel hangars added massive amounts of weight and radically altered the ship's aerodynamic profile, increasing its radar cross-section and forcing engineers to remove the dedicated Harpoon anti-ship missile launchers to save topside weight. The heart of the destroyer's incredible lethality, and the primary reason it commands so much respect on the global stage, resides in the Mark 41 vertical launching system. Instead of older mechanical rail launchers that required a terrifyingly vulnerable reloading process above decks during combat, the vertical launch system is a modular grid of missile cells sunk deep into the fore and aft decks. The Flight II Alpha variants carry 96 of these cells, protected beneath thick steel hatches that only blast open a fraction of a second before a missile ignites and roars out of the ship. When a weapon fires, the immense pressure and heat of the rocket motor exhaust are vented upward through a specialized internal plenum chamber, a violent sequence that subjects the internal steel of the ship to extreme thermal shock and acoustic pressure. This 96-cell magazine allows the commanding officer to carry a highly tailored mix of munitions, blending Romeo India Mike. 162 Evolved Sea Sparrow missiles for short-range defense with long-range Tomahawk land attack, cruise missiles for striking targets far inland. For ballistic missile defense, the ship carries the massive Standard Missile-3, a weapon capable of striking targets in the vacuum of space, while the Standard Missile-6 provides unparalleled capability against supersonic aircraft and maneuvering anti-ship threats. Yet, despite this overwhelming firepower, the vertical launch system introduces a terrifying operational reality. Once those 96 cells are empty, the ship is effectively disarmed. Reloading these massive weapon canisters at sea using cranes proved so dangerous and impractical in anything but a dead calm that the Navy removed the underway reloading equipment entirely, meaning an empty destroyer must abandon its combat station and return to a friendly port to rearm. To manage this complex choreography of sensors, propulsion, and heavy weaponry, the tactical brain of the ship operates deep within the hull in the Combat Information Center. This darkened room, illuminated only by the blue and green glow of dozens of tactical display consoles, is where the commanding officer and the tactical action officer make split-second decisions that can mean the difference between life and death. The Aegis display system synthesizes data from the main phase array radars, the hull-mounted SQS-53 bow-sonar dome, and the towed acoustic arrays trailing thousands of feet behind the ship to create a unified picture of the battle space. It is an environment of intense, high-stakes pressure where sailors must filter through hundreds of radar tracks, commercial shipping transponders, and biological noise to identify a stealthy adversary creeping into missile range. Knowing what you now know about its performance in heavy seas and the immense pressure of operating these systems, do you think the design trade-offs were worth it? Share your thoughts below. Stepping out of the air-conditioned, high-tech sanctuary of the Combat Information Center reveals the harsh saltwater reality of operating a complex steel machine in the unforgiving marine environment. The theoretical specifications of shipyard brochures quickly collide with the relentless corrosive power of the open ocean, where every exposed steel surface is under constant attack from salt spray, humidity, and microscopic marine life. Sailors spend countless grueling hours on deck utilizing needle guns, wire brushes, and heavy marine epoxy in an endless, backbreaking war against rust and structural degradation. When a destroyer spends 10 consecutive months deployed to the highly contested waters of the South China Sea, the maintenance schedule inevitably slips, and the pristine gray warship frequently returns to port, streaked with deep red rust, looking more like an abandoned freighter than the vanguard of American naval supremacy. This grueling operational tempo takes an enormous toll not just on the metal hull, but on the human beings required to keep the machinery running under extreme psychological and physical stress. The Pacific Fleet demands constant presence to deter adversaries, resulting in relentless deployment cycles that frequently force crews to work 100-hour weeks while surviving on broken, deeply fragmented sleep schedules. The horrific reality of this chronic crew fatigue was laid bare in the summer of 2017 when the destroyers Fitzgerald and John S. McCain were involved in separate, catastrophic collisions with commercial merchant vessels. These completely avoidable tragedies, which claimed the lives of 17 American sailors, exposed how pushing a complex, technologically maxed-out warship through heavily congested shipping lanes with an exhausted, sleep-deprived bridge crew leads to catastrophic breakdowns in situational awareness and basic seamanship. Despite the human and structural exhaustion plaguing the fleet, the relentless advance of enemy missile technology forced the Navy to upgrade the Burke class once again, leading to the creation of the Flight III variant. The central feature of this new variant is the installation of the Alpha Nook Sierra Papa Yankee 6 active electronically scanned array radar, a sensor so powerful it represents a generational leap over the legacy systems. Unlike the older passive radars that relied on a single massive transmitter deeply buried in the ship, this new active array is composed of thousands of individual solid-state transmit and receive modules that generate their own radar energy directly at the panel face. This provides unprecedented sensitivity, allowing the destroyer to detect and track incredibly small, stealthy targets, such as low-flying cruise missiles or distant drone swarms with pinpoint accuracy. But to power this overwhelming radar array, the designers had to face the terrifying reality that the Arleigh Burke's electrical grid and cooling systems were already operating at their absolute maximum capacity. The new radar demands exponentially more electricity than the legacy systems, forcing naval architects to replace the 3 older generators with massive, highly advanced Rolls-Royce 4-megawatt turbine generators. Pumping that much raw electrical power into solid-state radar modules generates a stupendous amount of waste heat, which meant the ship's internal air conditioning plants had to be entirely ripped out and replaced. The Flight III destroyers now carry massive cooling plants capable of generating thousands of tons of cooling capacity, pumping oceans of chilled water up into the superstructure just to keep the new radar arrays from melting themselves into useless slag. This cascade of upgrades, the heavier radar arrays, the larger generators, the massive cooling plants, has finally pushed the physical hull form of the Arleigh Burke to a critical breaking point. Every time you add tons of heavy equipment high up in the superstructure, you raise the ship's center of gravity, which inherently reduces its metacentric height, a vital naval architectural metric that determines a vessel's ability to remain upright. The Navy has been forced to meticulously shave weight from every possible corner of the ship, utilizing lighter composite materials for exhaust stacks, and removing legacy equipment just to maintain a bare minimum margin of safety against capsizing. There is simply no more weight allowance left. The ship is physically full, and any future addition to the combat system will require the removal of an equally heavy component, an impossible zero-sum game for modern naval engineers. The lack of excess electrical power and weight margin has effectively locked the Arleigh Burke out of the next major revolution in naval warfare: the deployment of high-energy directed energy weapons. As the threat of cheap mass-produced suicide drones becomes a dominant factor in maritime conflicts, the Navy desperately wants to equip its destroyers with powerful laser systems that can melt incoming targets at the cost of only a few dollars per shot. However, a weaponized laser capable of destroying a hardened drone requires sudden, massive surges of electrical power that the Burke's current generator alignment simply cannot provide without risking a catastrophic blackout of the ship's combat computers. While some low-power optical dazzlers have been fitted, the dream of a heavily armed, laser-equipped Burke is mechanically impossible, leaving the ship heavily reliant on its finite magazine of multi-million-dollar interceptor missiles to shoot down incredibly cheap rudimentary drones. This crisis of capacity becomes even more glaring when the Arleigh Burke is compared to the contemporary rival vessels it is expected to face in a high-end maritime conflict. The Chinese People's Liberation Army Navy has rapidly deployed the Type 055 destroyer, a massive surface combatant that dwarfs the Burke in sheer displacement and physical dimensions. The Chinese vessel carries 112 vertical launch cells compared to the Burke's 96. But more importantly, its larger hull provides vast margins for future electrical generation and sensor upgrades. Because the Type 055 is essentially built to the dimensions of a traditional cruiser, it does not suffer from the same cramped top-heavy weight restrictions that are currently strangling the modernization efforts of the American destroyer fleet. The tragic irony of the Arleigh Burke's current predicament is that it was never supposed to be fighting on the front lines in the 2020s. It was supposed to have been replaced by an entirely new generation of stealth warships. The incredibly ambitious Zumwalt-class destroyer was designed to be the future of the Navy, featuring a radical tumble-home hull, fully integrated electrical propulsion, and massive power margins specifically designed to field future railguns and laser weapons. But when the Zumwalt program collapsed under the weight of staggering cost overruns, technological failures, and changing strategic priorities, the Navy was forced to cancel the fleet and order more Arleigh Burkes. The aging workhorse was drafted back into production, forced to accept high-tech systems it was never initially designed to carry, simply because the Navy had no other functional surface combatant ready to build. Faced with this inescapable dead end in naval architecture, the Department of Defense has finally acknowledged that a clean-sheet design is absolutely necessary, leading to the development of the future guided missile destroyer program known as DDG-X. This future ship will abandon the cramped, exhausted Burke hull form in favor of a much larger, beamier structure that prioritizes internal volume, massive electrical power generation, and vast margins for future technological growth. The new ship will likely carry the exact same combat systems, radars, and weapons currently flying on the Flight 3 Burkes, but it will place them in a hull that actually has the physical space to let those systems operate efficiently, until that new class of ship slides down the slipway and joins the fleet in the next decade. The Navy has no choice but to continue relying on its heavily burdened, maxed-out workhorse to maintain sea control. Ultimately, the legacy of the Arleigh Burke-class guided missile destroyer is one of unparalleled success achieved through sheer engineering stubbornness and the remarkable resilience of its crews. It is a warship that outlived its intended lifespan, defeated its own high-tech replacement, and continuously evolved to meet threats that its original designers could not have possibly imagined. It stands as a monument to late 20th century industrial might, a vessel that perfectly balanced the demands of firepower, survivability, and mass production. But the ocean is an unforgiving environment that eventually claims all machines, and the laws of physics dictate that you can only cram so much capability into a steel box before the box simply cannot take any more. The Arleigh Burke has been pushed to the absolute limit of what a naval platform can achieve, and it will go down in maritime history as the defining surface combatant of its era. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.